This video deals with consonance and dissonance between pure tones whose waveforms have equal amplitude and phase. In the description of this video, a link is given to a Wikipedia article titled Consonance and Dissonance, which is a very good reference to how these concepts have evolved, their classification, and the different theories as to how they originate. The notion of consonant and dissonant harmonic intervals is of utmost importance in music theory, and in fact in two of the first theory videos incorporated in this channel, the videos Musical Notes, Part 1, Pentatonic Scale, and Musical Notes, Part 2, Chromatic Scale, whose links are given in the description. An experiment was performed with a simple two-stringed instrument, the first with fixed tuning to 261 Hz C, and the second with variable tuning to select the frequencies, notes. That produced a pleasant, harmonic, consonant sound with the first, which gave rise to the 12 musical notes used in Western culture. Among the theories mentioned in the article Consonance and Dissonance, whose link has been provided in the description of this video, we will use the critical bandwidth theory expounded in the paper Tonal Consonance and Critical Bandwidth by Plump and Levelt, which is available in PDF format in a link given in the description of this video, in which these authors conclude the following. The investigations indicate that, as a function of frequency, the transition range between consonant and dissonant simple tone intervals is related to critical bandwidth. These intervals are evaluated as consonant for frequency differences exceeding critical bandwidth, whereas the most dissonant intervals correspond with frequency differences of about a quarter of this bandwidth. In the figure shown on the left of the screen is a reproduction of Figure 10 of this article, which illustrates this fact. The concept of critical bandwidth is very well explained in the article La percepción acústica, Física de la audición, Acoustic Perception, Physics of Hearing, by Merino and Repiso, which is available in PDF format in a link given in the description of this video. The two figures on the right are reproductions of figures 7 and 9 of this article. In the continuation of this video, we will conduct simulations to verify what Plump and Levelt stated, and for this we will take as low frequency the reference law of 440 Hz. In the figure below right, the red dashed lines indicate that for this frequency we have a critical bandwidth of approximately 105 Hz. The screen shows the superposition of two sound pressure waves of equal amplitude and zero phase, in which the frequency of the second is twice the frequency of the first. This gives an interval of 1 octave. In the rest of this study, the equal amplitudes and zero phase will be maintained, but the frequency of the second wave will be varied. A color scheme has been used to facilitate the identification of these waves. The first is shown in red, the second in green, and the superposition of both is shown in black. Note that the resulting wave is not a pure sinusoid, but it has smooth variations, so, as we will see later, for this octave interval you have a nice, consonant sound. Note that the period of this wave is equal to the period of the lowest frequency wave. Let us consider a second case, in which the frequency of the second wave is close to that of the first, at 1.12 times its value. Although the figure representing the superposition of the two waves can be obtained directly from the expression of their sum, it is convenient to perform a trigonometric transformation to express this superposition as a product in which the first, cosine, factor depends on the frequency difference between the two waves, and the second, sine, factor depends on the average frequency of the two waves. The resulting waveform shows that the cosine factor controls its amplitude and the sine factor its frequency. This resultant is a complex sound wave which, as we shall see later, constitutes an unpleasant, dissonant sound, which introduces a tension. We will now consider, in ascending order of frequencies, several intervals, evaluate their degrees of consonance and compare this evaluation with that given by the curve of consonance and dissonance given by Plump and Levelt. We will not consider the unison interval, which has perfect consonance and produces a wave with twice the amplitude. We start with the augmented unison interval, minor second. Note that the first sound, as for the rest of the intervals considered, corresponds to the reference A4 of 440 Hz, and that the second one is a sharp 4, which has a frequency of 466 Hz, 26 more than the A4, which corresponds to an extension of 0.25 times the critical bandwidth of 105 Hz for this A4. Pay attention to each of the reproduced sounds, especially the one corresponding to the superposition. The result is a strong dissonance, as established for this frequency difference of 0.25 times the critical bandwidth by the Plump and Levelt consonance and dissonance curve. The screen shows the details of the reproduction of the major second, diminished third interval, in which the second sound is AB4, with a frequency of 495 Hz, 55 more than the A4, which corresponds to an extension of 0.52 times the critical bandwidth of 105 Hz for the A4. The result is a strong dissonance, although not as strong as that of the augmented unison interval, as established by the Plump and Levelt consonance and dissonance curve for a frequency difference of 0.52 times the critical bandwidth. The screen shows the details of the reproduction of the augmented second, minor third interval, in which the second sound is AC5, with a frequency of 523 Hz, 83 more than the A4, which corresponds to an extension of 0.79 times the critical bandwidth of 105 Hz for the A4. The result is an imperfect consonance, as can be seen in the Plump and Levelt consonance and dissonance curve for a difference in frequencies of 0.79 times the critical bandwidth. This is one of the most important intervals, since it is used in the construction of minor chords. The screen shows the details of the reproduction of the major third, diminished fourth interval, in which the second sound is a C-sharp 5, with a frequency of 554 Hz, 114 more than the A4, which corresponds to an extension of 1.09 times the critical bandwidth of 105 Hz for the A4. The result is an imperfect consonance, since it is close to the limit of the critical bandwidth, as can be seen in the Plump and Levelt consonance and dissonance curve for a difference in frequencies of 1.09 times the critical bandwidth. The screen shows the details of the reproduction of the perfect fourth, augmented third interval, in which the second sound is a D5, with a frequency of 587 Hz, 147 more than the A4, which corresponds to an extension of 1.40 times the critical bandwidth of 105 Hz for the A4. The result is a perfect consonance, since it is beyond the critical bandwidth of 105 Hz for the A4. The screen shows the details of the reproduction of the perfect fifth, diminished sixth interval, in which the second sound is E5, with a frequency of 660 Hz, 220 more than the A4, which corresponds to an extension of 2.1 times the critical bandwidth of 105 Hz for the A4. The result is a perfect consonance, since it is beyond the critical bandwidth of 105 Hz for the A4. This is one of the most important intervals, since it is used in the construction of major and minor chords. The screen shows the details of the reproduction of the major sixth, diminished seventh interval, in which the second sound is an F-sharp 5, with a frequency of 740 Hz, 300 more than the A4, which corresponds to an extension of 2.86 times the critical bandwidth. The corresponding sounds are reproduced next. The result is an imperfect consonance. This interval extends far beyond the value of 1.2, the critical bandwidth considered in the Plump and Levelt graph. For this interval and the rest of the intervals, we will limit ourselves to considering only our own evaluation and compare it with that of the article Consonance and Dissonance, whose link is given in the description. The screen shows the details of the reproduction of the major seventh, diminished octave, interval, in which the second sound is at G-sharp 5, with a frequency of 831 Hz, 391 more than the A4, which corresponds to an extension of 3.72 times the critical bandwidth. The corresponding sounds are reproduced next. The result is an imperfect consonance. The screen shows the details of the reproduction of the perfect octave, augmented seventh, interval, in which the second sound is an A5, with a frequency of 880 Hz, 440 more than the A4, which corresponds to an extension of 4.19 times the critical bandwidth. Next, we reproduce the corresponding sounds. The result is a perfect consonance. This concludes the study of consonances and dissonances between pure tones. Before moving on to the conclusions, it is convenient to recommend reading the Wikipedia article entitled Consonancia y Disonancia, Consonance and Dissonance, which you can access through a link given in the description of this video. In the historical review contained in this article, you will find the following. Kamioka and Koreagawa, 1969. The consonance between two pure frequencies, not between complex sounds, depends only on their remoteness and not at all on other factors such as proportion. This discovery was a certain revolution, since the fact that in musical sounds the proportion between frequencies does influence the consonance is due to the fact that natural sounds are not pure, but complex. End of quote. In the following theory video, we will deal with the study of consonance between natural, real sounds. If you are not familiar with the mechanism of hearing, the wonderful video entitled The Journey of Sound to the Brain, whose link is given in the description, will help you a lot to understand consonance and dissonance. In this video, we have studied consonances and dissonances between pure tones. This study is important because, although musical instruments and the human voice do not produce these pure tones, it will help you to understand the consonances and dissonances between real sounds, formed by the superposition of sets of pure tones. Thank you for watching this video. We hope you enjoyed it and found it useful.